everybody, I'm doing another read-along of this week's post. Thanks for stopping on by. What we have today is something called Design for Manufacturability, and this is the fourth part in the series on product development and design. Right off the bat, the idea of design for manufacturability sounds pretty intimidating. It sounds pretty technical and pretty wordy. And in fact, what we'll see in this article is some of the things actually are a little technical, but what I've come to realize is that's actually a lot of what my audience likes. Recently, I've been pleasantly surprised that everyone is interacting with a post on signal detection theory, of all things. So I'm going to try not to shy away from some of the more complicated and technical details. If it bores you or it's not your bailiwick, just let me know and I'll try to avoid that in the future. But really, I can only tailor my content based on what I'm hearing back. So if you like this, let me know. If it's too technical, let me know. If you'd like a different topic, I'm happy to take those requests as well. Anyway, we'll get into the read-along. Why design for manufacturability decides what your product actually costs. The culmination of product design shouldn't be a surprise. 3 articles into this series, we have built most of the system. We started with the customer using the Kano model and voice of the customer work to understand what people actually want and how much they care about each want. We then confronted the constraint landscape, the material and economic realities that force genuine trade-offs rather than wishful thinking. Last week, we covered quality function deployment and the house of quality, the structured methodology for translating customer language into engineering specifications without losing the original intent along the way. By the end of that process, a design team has a set of target specifications that are customer grounded, trade-off aware, and cross-functionally agreed upon. It would be reasonable to assume the hard work is done at this point. The customer wants and expectations are understood, the specifications are set, and engineering can now simply build the thing, right? That assumption is where a great number of products run into trouble without anyone noticing until it's too late, and it's the reason this final article exists. A specification that is technically correct and a product that can be manufactured reliably at volume at a sustainable cost are 2 different achievements. We kind of saw a shadow of this last week, by the way, as we were looking into quality function deployment, how we were aligning the product specifications not only to the customer wants, but then downstream also to the capabilities of the manufacturing environment. The gap between them is the subject of design for manufacturability, commonly abbreviated as DFM, and it is arguably the single largest determinant of what a product actually costs once it leaves the design phase and enters the real world of production. Design for manufacturability. Design for manufacturability is the discipline of designing a product with the realities of its production process in mind from the start, rather than treating manufacturing as a downstream problem to be solved after the design is finished. The core premise is straightforward. Every design decision, from the number of fasteners used to the tolerance specified on a critical dimension to the material chosen for a housing, has direct consequences for how difficult, slow, and expensive the product will be to build. This gets beyond just the materials, but actually gets to how the entire design is integrated into the manufacturing process. A design that looks sophisticated and elegant on a drawing can be a nightmare on the production floor because of the complexity. The difference is rarely visible to anyone who has not spent time thinking strategically about the system interactions of design and the tactical dimensions of assembly, machining, molding, welding, etc. This matters because cost is overwhelmingly determined and committed early in the design process, long before a single unit reaches the factory floor or the cost is actually incurred. The figure below, which I'll talk about in a moment, helps visualize this phenomenon. The commonly cited figure in manufacturing circles is that somewhere between 70 and 80% of a product's total manufacturing cost is locked in by decisions made during the design phase. Once a part geometry is finalized, a material is selected, and an assembly sequence is implied by the design, the cost envelope for the product is largely set. Everything that happens afterward, process optimization, supplier negotiation, lean manufacturing, can shave costs at the margins, but it cannot undo a fundamentally expensive design. This is why design for manufacturability can be an afterthought it's why it cannot be an afterthought bolted onto the end of the design process. By the time a design reaches a manufacturing engineer for review, most of the final financial outcome has already been determined by choices nobody on the manufacturing side was in the room for. So, what this diagram is here is on the y-axis. It's kind of like the percentage of total costs. We won't have a dollar amount associated with it. What we see is this second line here is actually like the manufacturing phase of when we actually start producing our first widget. And then we have kind of two lines, and on our x-axis, by the way, we have time. So essentially what we see is that about 40%, a little less than 40% of the design of the cost that we've committed to, that's this top line, the cost committed, happens when we're gathering specifications. And then between 40 and 80%, about big round numbers, happen in the design of the product based on the specifications, right? So we've committed to the designs, but we haven't yet really incurred those designs aside from kind of some tooling and so on down here to get ready for production. But then only 80%, or excuse me, only 20% from 80 to 100 of our cost is really varied in the production environment itself. And that's kind of like, the skilled labor, the workflows, the material handling, how much inventory we're carrying. Those are kind of the usual suspects we look at from a Lean and Six Sigma standpoint when we're trying to do process improvement. But we see that the cost that's incurred, well, now we're incurring it because we're actually building the things. We're building the widgets. But all of those things that we've committed to, that we're kind of locked into, happen, at least 80% of them happen in that design stage, in that initial stage. So that's why, though I'm a Lean and Six Sigma guy through and through, I like to focus so much on the design aspects of systems and the design aspects of products as well, because that's actually where the bulk of your improvement is going to come from. If you can get the design right, if you can decrease cost in the design phase, well, you're going to live that out through and through when you actually start producing the things. So that is a very important concept in product engineering and product design, is not necessarily what the cost is going to be in the design phase, but what it's going to be when we actually start producing them. Now, this should have been happening the whole time. This brings us to a point that deserves some more emphasis. Everything we are about to discuss in this article, the manufacturing constraints, the tolerance considerations, the assembly complexity, ideally should not be a discrete step that happens after specifications are finalized. It should have been a continuous parallel conversation running alongside the customer research, the trade-off analysis, the house of quality from the very beginning. The methodology that formalizes this is called concurrent engineering, and it represents a deliberate rejection of the traditional sequential design process. The traditional approach, sometimes called the relay race model or the waterfall model, has marketing hand a set of requirements to design hand a finished specification to manufacturing engineering, and manufacturing engineering attempt to build whatever arrives on their desk, right? So it's a series of handoffs from one functional department to the next. Each function works in isolation, completes its piece, and passes the baton forward. The problem with this model is that manufacturing feedback arrives only after the design is essentially frozen, at which point changes are expensive, slow, and politically difficult because reopening a finished design feels like a step backward to everyone involved. Concurrent engineering replaces the relay race with a standing cross-functional team that includes manufacturing engineers, quality engineers, and procurement specialists alongside the design engineers and marketing representatives present and contributing from the earliest stages of the product. The manufacturing engineer in this model is not waiting at the end of the line to inspect what arrives. They are sitting at the table during the House of Quality sessions, raising concerns about proposed tolerances before it gets written into a specification, flagging that a particular material choice will require a process the factory does not currently have, and suggesting alternative geometries that achieve the same customer-facing performance with a fraction of the assembly complexity. This does not slow the process down despite the additional voices in the room. It actually accelerates it overall because problems that would otherwise surface during a costly prototype build, or worse, during the early weeks of production, gets caught and resolved on a whiteboard instead. Toyota and the broader Japanese automotive industry pioneered much of this thinking, and it's one of the genuine reasons their products historically launched with fewer engineering changes and lower warranty costs than competitors who were still running the relay race. With this context established, the rest of the article walks through the specific manufacturing realities that a concurrent engineering team or a DFM review happening later than it should needs to confront directly. Now, one more caveat here. We have been focusing on kind of this design for manufacturing. There's actually kind of a whole thing we could do where we say design for X, where X can be anything we want to optimize for. And that's something that we just take hand in hand into the product development cycle. It doesn't have to be manufacturing. If we're building things that are very, very simple to make and manufacturing, we're not too worried about it, maybe we would do a design for procurement where we look at how we're going to get our materials, and we look at the sourcing, and we look at risks to supply chain and trying to decrease costs in the procurement process rather than the manufacturing. So the point here is that this design for manufacturability, which I know and love, and this is what I do a lot, which is why I'm talking about it, can actually be translated to any other part of kind of the operational chain of actually producing the widget, right? So it could be designed for supply chain. It could be designed for materials. It could be designed for procurement. Whatever we want it to be, these same principles are going to come through. I just happen to know a little bit more about design for manufacturability and design for assembly. So I'm going to walk you through that now. But just know that this principle can be applied to a variety of different functions across a business. Complexity skews and the cost of variety. One of the least intuitive realities in manufacturing is that complexity itself carries a cost independent of the complexity of any individual part. A factory that produces one product in one configuration on one line can run with remarkable efficiency. The moment a product line expands into multiple variants, the cost structure changes in ways that are easy to underestimate during the design phase. Every additional stock keeping unit, which we call SKUs, stock keeping unit, introduces overhead that has nothing to do with the physical difficulty of making the particular variant. Each SKU needs its own inventory tracking, its own forecast, its own safety stock calculation, and its own slice of warehouse space. A product line with 5 color options and 3 size options does not multiply complexity by 15 in a simple linear way. It creates 15 distinct items that procurement must source for, that production planning must schedule, and that the quality control must inspect separately, each with its own potential for being out of stock at the wrong time or overstocked at the wrong time. So again, we kind of see this systems dynamic playing through in a big way. If stock keeping units increase, the complexity of the operation does not increase linearly. This complexity compounds further when SKU proliferation requires the production line itself to change configuration repeatedly. We sometimes call these size changes or changeovers. Every time a line switches from producing one variant to another, it incurs a changeover, the process of reconfiguring tooling, adjusting machine settings, swapping components staged at each workstation, and often running a calibration batch before production resumes at full quality. Changeovers consume time during which the line produces nothing of sellable value, and that lost time is a direct cost that must be absorbed somewhere, either in higher unit prices or thinner margins. A design that requires frequent changeovers because of excessive product variety is, in effect, designing inefficiency directly into the cost structure before a single unit is built. Pretty straightforward there. Machine capability adds another layer of constraint that is frequently invisible to design engineers who have not spent time on a factory floor. A given piece of production equipment has a defined operating envelope. Sometimes we call that the optimal design domain. An injection molding machine has a maximum shot size. A stamping press has a maximum tonnage and a maximum part dimension that fits within its bed. A pick-and-place machine used in electronics assembly has a minimum component size it can reliably handle and a maximum board size it can index. A design that specifies a part just slightly outside the capability of existing equipment does not result in a slightly more expensive product. It often results in the need of entirely new capital equipment, a cost that can dwarf every other consideration in the project. Designers who understand the installed equipment base of the facilities that will actually build their product can design within the envelope and avoid triggering capital expenditure that was never part of the original business case. When I worked in the tire manufacturing industry, we had this instance happening where a number of customers were going for wider rim, smaller sidewalls on their tires. So if you look at tires built in the 1990s, they actually look very, very different than the tires we see today with a lower profile and a bigger rim. Well, the tire building machines actually had a limit to how big of a rim they could go up to and how small of a sidewall they could go up to. So actually, as consumer preferences changed, we had to totally overhaul all of the equipment in the assembly portion of the manufacturing plant because we were running into this capability constraint. Yes, we had the capacity to run it. We could run 36,000 tires a day, but we couldn't run the tires that the customer demanded. Tolerance stacking. If complexity and SKU proliferation at the macro level manufacturing concerns, tolerance stacking is the micro level concern that deserves equally serious attention. This is where it's going to get a little technical. Because it sits at the heart of a problem that is endemic across design organizations, designers quite reasonably optimize primarily for functionality. Does the thing actually do what I want it to do? The question that dominates the design process is whether the thing works. Does the assembly fit together? Does the mechanism move correctly? Does the part perform its intended function? This is the right question to ask at first, but is frequently the only question asked, and that narrowness creates serious downstream problems. As I was mentioning before, that design for X, sometimes it's just design for function. It's just, does the thing work? Without any considerations into design for manufacturability, assembly, procurement, supply chain, warehousing, any of these sorts of things. Every dimension on an engineering drawing carries a tolerance, a permissible range of variation around the nominal value, kind of that average value that we want. Because no manufacturing process produces parts at exactly their specified dimensions every single time. A shaft specified at 25 millimeters might actually measure anywhere from 24.95 to 25.05. So we've got, a range of 0.10 millimeters, depending on the precision of the machining process used to produce it. Individually, the small variation is manageable. The problem emerges when multiple tolerance dimensions are combined in an assembly, because the individual tolerances stack on top of each other, and the cumulative variation at the final assembly point can be far greater than any single tolerance would suggest. Now, I'm going to skip this paragraph because it's just a technical example. But what we run into is sometimes the issue is not that there's too much variation in the manufacturing process. The thing is that sometimes the tolerances are so tight that now they don't actually work together. So we're going to jump over now to value engineering. Value engineering. With the manufacturing constraints on the table, it becomes possible to talk about the disciplines that actively work to resolve them. The first of these is value engineering, sometimes practiced under the closely related banner of value analysis. Um, this role of a value engineer is to systematically examine a design and ask a question that is deceptively simple to state and genuinely difficult to answer well. Does this feature, component, or specification deliver value to the customer in proportion to what it costs to produce? Value engineering is built on a foundational idea borrowed directly from the Kano work in the first article of the series. Every dollar spent on a product attribute that the customer does not value, does not notice, or would not pay for is a dollar that could have been spent improving an attribute the customer genuinely cares about or simply returns to the business as margin. A value engineer looks at an overbuilt bracket holding a non-structural component and asks whether the wall thickness could be reduced without affecting function. They look at fasteners specified in an exotic alloy and asks whether a standard low-cost fastener would perform identically in the same application. They look at custom molded parts and ask whether a standard off-the-shelf component could be substituted at a fraction of the tooling cost. A few concrete practices define disciplined value engineering work. Functional analysis is the starting point, whether every component and feature is mapped explicitly to the function it performs, using the house of quality relationships from last week's article as a natural input. Components whose function cannot be clearly articulated are flagged immediately as candidates for elimination. Cost target allocation follows. When the overall product costs target are distributed across subsystems and components in rough proportion to the customer weighted importance established back in the Kano and Voice of the Customer work, so that the engineering effort and the material costs concentrate where the customer actually derives value. Okay, I'm going to stop reading. It's getting too technical here. Essentially, what we're trying to do is making sure that the part that we're trying to produce is proportional. The value that it's deriving to the customer is proportional to the cost we're incurring to produce it. That means if we have to do custom tooling to make this thing just right, we'll look at some standard things that we can get from a Grainger catalog, or some just standard brackets that we can import over from China, right? We'll look at how many different bends things will need in a bend brake machine, and see if we can't reduce the number of those things to reduce the labor costs associated with any individual parts. We'll also look at whether the thing is overbuilt in terms of the material specified, how thick the steel has to be. A hobby horse of mine right now is if you go and look at like steel brackets, or steel hinges for your doors in all of your houses, they're like super, super thick steel, right? There's there's so much strength on any of those brackets. You don't need something that strong to hold up, probably a hollow door on the inside of your house. And yet we're buying these things because they're just off the shelf. They're a little bit easier. So we can kind of see there's a trade-off between what's easy to buy off the shelf and is at low cost versus what's actually required from a tolerance standpoint and a functionality standpoint. And then if you ask yourself if let's say you have a 3D printer, do I really need a steel hinge for my door? Or can I just, put some filament into my 3D printer, build a hinge, and that'll hold up my door as well. So now I'm low cost because I've analyzed the tolerance, the materials, the specifications relative to my actual function. So that's essentially what value engineering is doing. It's making sure we have the right parts and the right complexity for the job. And if we do need complex parts, if we need custom moldings, if we need high precision stuff, well, then we better make sure that the customer actually wants it and is willing to pay for that, because that's costing us too. Another thing that we have here is design for assembly. This is actually like my favorite topic. The second discipline worth covering in detail is design for assembly, often treated as a subset of design for manufacturability, but it's important enough to deserve its own focus. The guiding principle behind design for assembly is part count reduction. Every individual part in an assembly represents a handling step, a potential orientation error, a fastening operation, and a quality check. A design that achieves the same function with 12 parts instead of 20 has eliminated 8 opportunities for assembly error and 8 operations that consume labor time, even before considering the reduced procurement and inventory burden discussed earlier in the article. Designers practicing good design for assembly habitually ask for every part in an assembly whether it could be combined with an adjacent part, whether it could be eliminated entirely, or whether its function could be absorbed into a part that already exists in the design. The name of the game here is simplify. A handful of concrete guidelines make this principle actionable rather than abstract. Parts should be designed to be self-locating, wherever possible, using features like chamfers, guide pins, or asymmetric geometry that naturally guide a part into its correct position and orientation, removing the need for a worker or robot to make a judgment call during the assembly process. Parts should be designed with Poka-yoke principles in mind, meaning the geometry itself should be made in physically impossible. Should make it physically impossible, or at least highly difficult, to assemble it incorrectly. Fastening methods deserve deliberate scrutiny, with a general preference for snap fits, integrated clips, and other tool-free fastening methods over screws and bolts, wherever the functional requirements allow it, since each screw represents a separate tool, a separate motion, and a separate point of potential failure during assembly. Symmetry should be used whenever function permits, because a symmetrical part can be picked up and installed without regard to orientation, eliminating an entire category of assembly error and inspection burden. Finally, access should be considered explicitly, asking whether a worker's hands, a robotic and end effector, or an automated tool can actually reach the location where a fastening or joining operation need to perform, since a technically simple assembly step becomes a costly bottleneck if it requires awkward access or excessive reach into a confined space. So again, the name of the game here is simplify. If we don't have to use a screwdriver and we can just snap things into place, let's go ahead and do that. If we can make something symmetrical so I don't have to orient it correctly, let's go ahead and do that. If I can guide any of these things into the correct location by maybe using a little bevel or, just using templates, using jigs, using color coding, whatever it takes, I'm trying to make assembly very, very fast. Not just for the hands, the dexterity of the assembler, but also for their mind, to make sure that they don't have to think and double check whether or not they're assembling it correctly. We can do so many things with this. I should do a whole series on design for assembly. Bringing the system together. Looking back across this entire series, a clear pattern emerges. Product design done well is not a sequence of independent decisions made by isolated functions and handed forward like a baton. It is a system with feedback loops running in every direction. That's good systems thinking. Where customer insights from the Kano model and voice of customer work informs the trade-off decisions, where those trade-off decisions get formalized and made traceable through the house of quality, and where manufacturing reality in the form of complexity costs, tolerance stacking, value engineering, and assembly design has to be present in the conversation from the very beginning, rather than arriving at the end to discover what nobody asked about. The products that succeed in the market over the long run are rarely the result of brilliant individual decisions made in isolation. They are the result of a design process that respected the full system, kept every function in the conversation throughout, and made deliberate, visible choices about where to optimize and what to trade away. That is the thesis of this entire series has been building toward, and design for manufacturability is where this thesis meets the factory floor, where every choice made on a drawing becomes a real cost, a real defect rate, and a real margin multiplied across every unit a company will ever produce. So that's the end of the article. It was free. Please subscribe, leave a comment, and share this publication, Systems of Human Performance, with just one friend. By the way, if you are a paid subscriber, I have, in my real work, in my consulting work, I've actually done a lot with design for manufacturability. and a little bit of AI augmented design. I've created a customer packet for one of my clients to share with their clients, with their customers. And what I've done is I've kind of reformatted this packet to be appropriate for the general audience that I have here on Substack. So if you're a paid subscriber, you can get this you can get this packet, excuse me. It has all kinds of tips and tricks about design for manufacturability, different workflows, RACI matrices on making sure people are doing the right things at the right times, process maps, and a number of checklists and tips and tricks on how to actually apply design for manufacturability and design for assembly into a real world operation. There's also several slides on how to use generative AI to guide and augment the product design process as well. So there's a number of things we can do with AI, and it's an exciting place to be applying this to product design. So that's there if you are a paid subscriber. If you're not a paid subscriber, I still appreciate your time, and I appreciate your interest in systems of human performance.